Hello, this is Mr. Craig, and I want to talk about more kinetics here. This is topic 8, part B, which is day 102 if you're in my class. Yesterday, or the last time that we met, we discussed the reactant orders for an individual reactant when we had more than one reactant. Again, to refresh your memory on that, the only type of order that we care about is a zero-order reactant, a first-order reactant, or a second-order reactant. And again, what a zero-order reactant does for us is that if we change the concentration for a zero-order reactant, the rate does not change regardless of what the concentration is. If we double the concentration for a first-order reactant, we double the rate. In other words, it goes twice as fast. For a second-order reactant, if we double the rate, it's exponential, which means it'll go 4 times faster. And then it'll work in the opposite direction too. So if we have half the amount, then that'll also be affected accordingly. Well, today what I want to talk about is the overall order for a reaction. So in our notes here it says overall order. If I have a reaction where, say, I have 3 reactants, and maybe the first one is a first-order reactant, the second one is a second-order reactant, and the third one is also a second-order reactant, we would add up the orders to get an overall reaction order. Now, those do not have to be 0, 1, or 2. And in that case that I just said, with the first order, second order, and another second order, the overall order for the reaction would be 5. So for an individual reactant, yes, you can only have 3 choices, or 3 choices that we care about for the AP exam. So when you are asked to determine the overall order for the reaction, add up all the orders. Alright, we talked about first order reactions or reactants the last time we spoke, and on the AP exam there's an equation that looks like this right here, and that's on your equation sheet, and you'll find that on the kinetics section on your equation sheet. I believe it's on the front side lower left hand corner. It's either the second or the third from the bottom corner. And what this is saying is that the natural log of the concentration of A at some point in time minus the natural log of the initial concentration, that's what that little 0 right there represents, and T represents some point along the reaction, is equal to the negative value of the constant K times T, which is the temperature. We could also write the equation to look like this, where the natural log of the concentration at some point in time over the initial, and that's saying the same thing mathematically speaking. If I take the natural log of A minus the natural log of A initial, then I can divide those out. So either way you want to work those, work that equation out, that's fine. There's nothing wrong with that. However, we have to realize what these variables represent. So again, the T is some point in the reaction, and typically what that means is how much still remains, and again the 0 is your initial amount. And we'll do some calculations here shortly to show how this works. One thing that I want to talk about is looking at the negative K here. The reason why that value has a negative value there, if we scroll down here, you'll see 2 graphs. The graph right here, the one on the left, actually shows a graph in representation of the natural log, the concentration of A versus time. And again, there's that deceleration or that curving slowdown, so to speak, of the reaction. In other words, it's always going to be quickest at the beginning, and then it slows down considerably near the end of the reaction because we don't have as many reactants. However, if I want to check and see if this type of reactant is a first order reactant, I can take the natural log of A versus time and it will yield a negative slope. There's my straight line. If I get a straight line with a negative slope here, then that means I have a first order reactant. So when I go back to my equation and I see negative K, my negative K is indicative of this negative slope. So on the AP exam, in the multiple choice section, you may be asked to determine what the order of a reaction is simply by looking at the graph itself. Now, it wouldn't be fair for you to be asked a question where it says the concentration of A versus time and you see a deceleration, because that could represent both first or second order reactants. Now, it would not represent a zero-order reactant. Remember that a zero-order reactant does not change the rate based on the concentration. So if I had, say, just the concentration of A versus time, then that would generate a negative slope. But that natural log there tells me that's a first-order reactant. Half-lives. Typically when we talk about half-lives, most half-lives that we deal with, especially with like nuclear reactions or a lot of other reactions, typically are first-order reactants. Half-life, again, tells me it's an amount of time that it takes for half of the amount that we started with to decompose or to disappear or to change into products. So whatever that amount of time is, that time will remain the same for each half-life. So in the graph here, I have, looks like about 100 days is the half-life period. In other words, I started off with, looks like 0.1, and then after 100 days I had 0.05. After another 100 days, I would expect there to be 1/2 of that 0.5, which would be, in this case, be around 0.025. And then after each 100-day period, I would expect there to be half of the half. So we can do some calculations knowing what the half-life is. We can determine how many half-lives this has gone through. We can determine how long it takes to reach the half-life. We can actually calculate a couple other things based on that. I don't want to give that away just yet. So when we do a half-life calculation, there's a shortcut here. I mean, yeah, you can take the 0.693. What that is if you look at your equation here, actually it's a little simplified, and I don't really like to show this equation in class, but if I take the natural log of half of the concentration over 1, then that will give me, natural log of that will give me a negative 6.93. Now that negative value up here is because I have a value that's less than 1 for the natural log. However, the negative k down here is where I bring that negative k down below the 0.5 over 1, and then that'll give me my half-life time. So whenever I work these types of problems out in class, you will always see me put 0.5 for that concentration. I will not use this 0.693. I don't want you to have something else to memorize. I would rather you be able to use this equation. Some of you may be able to remember that number, and that's fine. Just as long as you're showing your work and showing all your steps, the graders will be happy with you. But if you just go ahead and type that information in and write the answer down, you probably won't get any credit for it. So again, always show your process here. Continuing on here, I'm just showing the process of how I work out a half-life problem, and I'm going to do one like that here momentarily. So I think that concludes the first sheet here, and this one was mainly dedicated to first-order reactants, even though I have second-order on there. Examples part 2 will discuss second-order reactants. So let's take a look at that video. Hello, this is Mr. Craig, and I want to talk about examples part 2 for day 102. And even though the heading here says first-order reactions and half-life, primarily this discussion will go over second-order reactions where there's one reactant. Again, what we talked about on day 100 is a second-order reactant. This equation, which is on your equation sheet, again, it's located on the front side of your equation sheet underneath the Kinetics heading, bottom left-hand corner. This is the equation we want to use for a second-order reactant, where there's only one reactant, so the reaction is a second order. What this is, it's 1 over the concentration of our substance at some point in time minus 1 over the initial concentration is equal to a positive K times T, which again, that K is your constant and T is the temperature. I'm sorry, temperature is time. So the T is the time here. If we wanted to determine whether the reactant was a first order or second order, that's why I have on here, again, just like on the last video, we want to look at the graph. The data will tell us whether or not we're looking at a first order reactant or a second order reactant. Based on the last video, if I took the natural log of our concentration and plotted it versus time, it would yield a negative slope. Recall that the equation had a negative K. However, if I decide to take the natural log of the concentration for a second order reactant versus time, it will yield a slightly curved graph here. And again, that's not a straight line, so that tells me that cannot be a first order reactant. The way we get a that we get a straight line with a second order reactant is by taking the inverse of the concentration versus time. In that case, that will generate a straight line with a positive slope. So when we go back to our equation here, that's why when we look at our equation, it has a positive K, because it has a positive slope when we take the inverse of that concentration. So the equation itself should be able to help you determine what type of graph you should be looking at to determine the order. So again, this graph over here on the left represents a first order reactant, and the graph here on the far right represents a second order reactant. Do recall that if you do have the natural log of the concentration versus time and it yields something that's sloped, you're looking at a second order reactant. But to be honest, I don't ever recall seeing a question like that on the AP exam. We always want to be concerned with the straight line, so whether it's a negative slope or positive slope. And I'll talk about the zero order graph, I believe, on day 103. But if you want to get the sneak preview here, the spoiler alert, it would be a negative slope, but it would just be concentration versus time. You would not have that natural log there. Because again, remember, a zero order reactant doesn't care what the concentration is, the rate remains the same. Alright, for determining half-life, actually this is probably one of the simpler equations to determine the half-life. All I need to do is take the inverse of 0.5 minus 1 over 1, and we'll do an equation like this here very shortly. But again, don't try to memorize an equation like this to help you with a half-life. It's best to plug in the values. And again, that's my own personal opinion. I'm not somebody that likes to go out and memorize things. But it does make it a whole lot easier if you just say, okay, I'm going to make the concentration at this point in time 0.5, and the initial is 1. Trust me, it will save you a lot of anguish and heartache here. So we'll do some calculations with that here in a second. And I think that's all I want to say about this one. So the graphs primarily are the big topic here that we care about on this one. Okay, let's go work some problems out in the next video. Hello, this is Mr. Craig, and I want to discuss some of the calculations here on examples part 3, day 102. The first question says that a certain first order reaction is 73% complete in 110 seconds. The question wants us to determine the rate constant and the half-life for this process. Now, a couple things that we want to really focus on here is, first of all, we know that we have a first order reaction. Also, we know that we have 73% that is complete. In other words, 73% of our reactant has had a chance to react and form products. And we also know that the time involved for this reaction to get to 73% completed has been 110 seconds. Now, one thing that we want to do is, first of all, recognize which equation we're going to use. So since it's a first order reactant, we want to use the natural log of the concentration at some point in time over the concentration that we originally started off with. Now, since we don't have any molarity values here, it just gave percentages. Go ahead and pretend that you're working with a 1 molar substance. That's a little easier to work with or manipulate with. Also, to complete this equation, we know that we are using the equation that has a negative K times the time here. And again, we know it's a negative K because if we look at our graphs and we plot this thing out versus time, if it's a first order reactant, we should have a negative slope. And again, that's what that negative K is indicating for us. So let's go ahead and erase that. Oops. So we know that we should recognize that we're using the correct equation because it has a negative K, and that's what we would expect if we took the natural log versus time. Alright, so if we know that we're 73% complete, what that means is we have 27% of our reactant remaining. And that's the value that we have to plug in for our concentration at some point in time. So knowing that, let's rearrange the variables here so that we can isolate what the K value is, because that's what the first point, or the first question's asking here. So you'd find the rate constant, and you need to know the rate constant before you can do anything else with this. So let's rearrange this. We're going to move the T down below. So the equation will now look like natural log of the concentration at some point in time over our initial concentration. Again, all over that. And I'm going to bring the negative sign over as well, just to clean things up. And that'll equals K. Again, to simplify this, go ahead and make this value 1 molar. So if we have a 1 molar solution and we only have 27% of that remaining, what does that value actually represent? Well, to be a decimal would be 0.27. So I'd have natural log of 0.27 over the negative time, which again is 110 seconds. And if I type that all in, let's go ahead and get a number here. So natural log of 0.27 divided by negative 110. So I get a K value that's equal to 0.0119. And the unit for this is 1 over seconds. So there's my K. That should say seconds. So that's my K value. That's my constant. So throughout this whole reaction, that is my constant, or my slope if I were drawing that out. Okay, so that would be, oops, erase there. Alright, so we answered the first part. We got the rate constant out of the way. Now it wants us to determine the half-life for this. And again, recall that when we talk about half-life, we're talking about an amount of time needed to get to half the concentration that we originally started with. Well, let's go back up to this equation here. This is our equation that we rearranged here. Since we're looking for the time, let's go ahead and move it back and move K down for our half-life reaction. So that means that we're going to have the natural log of 1/2 over 1. So I'm not going to go ahead and write the 1 there. And we know that our K value is this over here. So 119, and put the unit second on the opposite side. We don't want to have two dividing lines here. And this will give us our amount of time, because again, our unit that's left will be in seconds. So if I take the natural log of 0.5 and divide it by the negative answer from the last question where we had K, that number's still in your calculator, it'll give you a nice time here, which is 58.2 seconds. Now, let's think about this. Does that make sense, or does that seem like a logical answer? Well, if we come back up here and we look at the question, it says that we've consumed 73% of that in 110 seconds. Well, that number that we get for the half-life, our half-life value, better be smaller than 110 seconds. So, yeah, it looks like we did our math right, and that does seem correct here. I'm going to go ahead and make a couple more videos for each of these examples, and I hope that this has helped. This is Mr. Craig, and I'm going to go over example question number 2 from the examples from part 3 on day 102. So we already worked out example number 1. That's on the previous video here. So let's go right to example number 2 here. Again, this question says that we are looking at a first order reaction. Okay, it's a first order reaction, very important. Says that it is 20.5% complete and our time is in 200 seconds. So again, that represents our time. 20.5% complete tells us how much of the reactant has been reacted. And again, the first order tells us what type of equation we're going to use for this. Now, first of all, let's make sure that we know how much is still remaining after 20.5% has been consumed. Well, if you have 20.5%, that means that we still have 79.5% of the reactant remaining. Okay, so that means that this is probably a pretty slow reaction if only 20.5% of that has been consumed in 200 seconds. So it's not as fast as our last reaction, which is fine. All right, so the equation that we're going to use again is our natural log of the concentration. And again, A is just a generic term here. At some point in time over our initial concentration is equal to negative K, again is our constant, which we will be determining here in part A. So again, we want to rearrange this because we're looking for the K here. So we're going to move the T down below. So we'll have our natural log of A at some point in time over our initial concentration originally. And that'll be, and I'm going to bring the negative with that. Again, this gives us a cleaner value. So we'll be able to calculate K from that. Now, we can go ahead and do the calculation here. I'm going to scoot that over just a little. Since we have 79.5% remaining, and I, again, make it with a 1 mole solution, makes your life a lot easier. I'm going to take the natural log of 0.795, because that equals 79.5%. And I'm going to divide that by my negative time, which in this case is 200 seconds. So my unit for this, kind of getting a little squirrely there, is going to be 1 over seconds, and whatever that value is equal to. So let's calculate that real quick. So the natural log of 0.795 divided by negative 200. So that gives me a value of 0.0, we'll go 0, 2 zeros, and 115. Okay. So there's my my constant for the reaction for all 3 of these situations here. Okay, so once I have what my K is, then I'm ready for part 2, or part B, that says what is the value at the half-life. So again, we want to, if we're using half of it, then that means that we have half our concentration, so 0.5. And again, I want to have the T and the K switch places here, since we know what the constant is, and we're looking for our time. So I'm going to have the negative K, which is equal to my time, which is my half-life time. And so I'll type that in as 0.5 over my negative 0.00115. And again, put the unit seconds on the opposite side just to keep it clean. And I still have my value for K in, which is actually 0.001147065. So I'm going to leave that in. I'm actually going to take the negative answer and then take the inverse of that and multiply it times natural log of 0.5. And that gives me 604 seconds. So 604.278, but let's go with 3 sig figs. So there's my amount of time that it takes to get halfway, or to use half of the substance. Now let's take a look at this. Does that make sense? Well, to go 20.5%, it took 200 seconds. So that was a considerable amount of time. So yeah, 604 is a good answer here. All right. And then it asks how long will it take for the reaction to go 45% and 85% completion. So that means that for 45%, that means I have 55% of the substance remaining. And for 85%, that means I only have 15% remaining. Okay, try to work that one out on your own. I'm going to quietly work it out here. Just show the work here. I'm not going to necessarily talk through this. So I'm going to do the 55% remaining first. And my K remains the same. Sorry, I spoke up. Put my time up here. So that'll give me my first scenario. So natural log 0.55 divided by negative 0.00115. So that's around 520 seconds. And then the other one is 15% remains. 115. Again, put your seconds up top. Oops. So natural log 0.5 divided by negative 0.00115. So around 1,650 seconds. Okay. Hope these are getting easy for you. If you know how to rearrange the variables and use your natural log, I think these are going to be really fun questions for you. And hopefully we'll see something like this on the AP exam this year. This is Mr. Craig, and this will be the third and last video for this example sheet, part 3, day 102. The first two examples already talked about example problem number 1 and example problem number 2, which are both first order reactants or reactions. Looking at the back side of this, we have example number 3, which states that we have a certain second order reaction, and again that's pretty important. Oops. And let's get the pen working here. So, we have a certain second order reaction, and it says that it is 67% complete, and it has taken 27.3 seconds to consume 67% of this reactant. Question wants us to determine the rate constant and the half-life for this reaction. Alright, so first of all, recognizing that we have a second order reaction, we're going to use a different equation than the one that we've been using for first order. And this looks like this, where we have the inverse of the concentration at some point in time minus the inverse of the initial concentration. And that's all equal to K, which is positive, times our time. Now, the reason why we have a positive K here is, recall from earlier on in the discussion, that if I take the inverse of the concentration versus time, this is how I generate a positive, and that's a straight line I just drew there, a positive slope, which represents my K value. So the K will always represent the straight line, whether it's a negative or a positive slope in this case. Okay, so let me erase this. Okay. So that just is a little bit of a refresher and an easy way to remember which equation you wish to use on something like this. Alright, so we have our equation, and now we're ready to plug in our values here. So first of all, we need to first of all determine the rate constant. So that means that we need to take our time and bring it down here. So now our equation will look like this, where the concentration at some point in time minus the initial concentration is equal to K, and then the time is below it. And again, that is a positive value. So what we want to do is figure out what our concentration is at some point in time. Well, that's what this is going to help us do. So if we've used up 67%, or 67% complete, how much of the reactant remains? Well, it should be around 33%, if I do my math right. So if we know we have 33%, and again, doesn't say what the molarity was, so go ahead and assume it to be a 1 mole solution. So I'm going to take 1 over 0.33, and I will subtract that from 1 divided by 1, because my initial concentration was 1 here, and then I will took 27.3 seconds to consume that amount, so I'll put my seconds down below here. And again, that should equal a positive value. Now, what's really cool, if you want to do some of that math in your head, if you take the inverse of 0.33, the 0.33 really is 1 over 1/3. Now, again, if you take the inverse of the inverse, that equals 3. Okay, so and if you want to do this on the calculator, I am not opposed to that. Actually, it'll keep you out of a lot of trouble here. So, the inverse of 0.33 actually equals 3, minus 1 divided by 1 is 1, so 3 minus 1 is 2, and then divide that by your time, which is 27.3 seconds, and that will give me my K value. So let's do 2 divided by 27.3, and that gives a K value of 0.07, we'll say 33. Okay, and it really doesn't matter how far you go out. Just show at least 3 sig figs. On the AP exam, they're always going to be looking for something like that, and of course, always show your unit. So it'll be 1 over seconds, and for the most part, K will always be 1 over some time, which makes sense here. All right, so there's our K value, and again, that equals our K. So now we're ready to answer the next part where it says the half-life. So again, using this equation here, if I'm using half-life, then that means I have half of my original concentration. So knowing that my K value is right here, I'm going to do 1 over, I'm going to scoot this down a little bit, 1 over 0.5 minus 1 over the amount that I started with. And again, I'm going to switch the T and the K here, since I now know what my constant is. And so I'm going to have over K, which is equal to my half-life time. So again, the inverse of 0.5 is just like saying that I have 1 over 1/2, which is equal to what? 2. So, and again, you don't have to do it that way, but if you need to. So I'm going to have 2 minus 1 over the K value, which is 0.733. And again, the unit's 1 over seconds, so put seconds in the correct spot. So whatever 2 minus 1, which is the inverse of my K value, so you have that in your calculator, hit the inverse button, and it says it's 13.65 seconds. I'm going to make that 13.7 seconds for 3 sig figs. And then you need to ask yourself, does that answer seem logical? Well, coming back up here, for 67% of the reaction to be complete, it took 27.3 seconds. So my answer should be less than 27, and it is. It's 13.7 seconds. So yeah, that seems like a very good answer. I hope these 3 videos have really helped you on understanding how to do first and second order reactant problems with these equations that involve natural logs. If you see, or if a kinetics question is asked on the AP exam, I guarantee you will see something that looks just like one of these 3 problems. And as always, I hope these videos have helped.